if the domain of our function is described in polar coordinates, we can still calculate some units of volume here as before and then add them all as we did it in the general domains. The distance here is just a distance in the line, so it's going to be the difference between r here and r here, so this is going to be just the dr. But the length of these are not straight, these are arcs. That is, we have a angle here theta, so then the length of this arc is going to be the radius multiplied by the angle. So the differential here is going to be not just the theta, but it's going to be multiplied by r. So that will make a difference here where we put r multiplied by the theta. And so the double integrals in polars is going to be given by the additions of the values of the functions, but multiplied by r and then dr d theta. So Fubini's, again in the version for polar coordinates, is going to tell us that if the region is rectangular in polars, meaning that the region is limited by two straight lines and two arcs here, where the angle vary between alpha and beta and the distance vary between A and B. So in those cases, so we can calculate the double integral by putting the function multiplied by r dr d theta and then putting the variation of each ones in any order when they are constants. For example, let's calculate the double integral of this function when r is the interior of the circle of radius 1 in the first quadrant. So we have to first identify this domain. So let's put the Cartesian coordinate for reference, and this is going to be a circle of radius 1. So here is 1. This is a circle of radius 1, and we are going to consider the interior of it, but only in the first quadrant. So the region of integration is going to be this one here. Okay? So we can describe this region in polars. So the description will be that the radius vary between 0 and 1. And the angle vary between the angle 0 and the angle pi half. So that's the variation of the angle. So we have the description then of the region in polars. And so the double integral over this region of the function dr dA is going to be equal to the double integral, and remember that here we need to put the function er squared times r dr d theta. And so now we are going to say that this is the integral between, and so the angle is going to vary between 0 and pi half, and this is going to be the theta, and the radius r is going to vary between 0 and 1, and so we have that the function is er squared r dr. And as always, we are going to leave this one for the end, and we are going to start by solving whatever is between parentheses. So this is going to be equal to the integral 0 pi half, and we leave the theta outside. And inside, we are going to write down this integral. So first, we calculate the primitive of e to the r squared r. Well, for that, in order to calculate the primitive, we're going to calculate the primitive separately. Remember, when there are extremes involved, we need to calculate the integral separately. The primitive of e r squared r dr is going to be, by doing the change of variable, r squared equals u, 2r dr equals du, and so dr equals du over 2r. So we're going to change this and this in this integral, and becomes the integral of e to the u times r times dr, and dr is du over 2r. Now r and r cancel, and this is 1/2 the integral of u, which is u again. And doing the change of variable, this is 1/2 e to the r squared. And in this way, we calculate that the primitive of this is this. And so then we can just write down the primitive here. The primitive is then e to the r squared over 2. That's the primitive of this function. And now we're going to evaluate between 0 and 1, and we're going to do the dr. And so this is equal to this integral. And so this evaluation is going to be e to the power 1, just e over 2, minus e to the 0, which is 1 over 2. E minus 1. And so we see that everything here is a constant, right? And so we take the constant outside of the integral, and we integrate just d theta. And so this is 1/2 e minus 1 theta evaluated between 0 and pi over 2. And so this one is 1/2 e minus 1 pi half minus 0. And so the final answer is pi over 4 e minus 1. So this is then the double integrals of this function. And when the region is more general, it's not rectangular as before, I mean, like if the r, instead of vary between two numbers, vary between two functions, we are going to still be able to calculate the integral as we did in the rectangular case. I mean, if we have that the two angles are fixed, but then r vary between this function and this other function, so we can still calculate the integral over here by putting the one that is constant outside, and so the ones that vary between the function g1 and g1 we do second. For example, let's calculate the integral of this function where d is the interior of the cardioid. So let's do a graph of this one. So if we have this cardioid 1 plus cosine of theta, so we're going to consider just the part in the second quadrant, so that will be only this part here. Okay, so we have to integrate then this function in this region, so we can see now that the variation of r is not going to be from one constant to the other as before, but is going to vary from one constant but to one function. Now this one is vary, so here is different, right? So they're all different r's here. Okay, so let's describe the variation of r and theta. So we have that r is going to vary between 0 and this function, which is r equal 1 plus cosine. And the angle is going to vary from here to here. So it's going to be varying from pi half to pi. Once that we have the domain described in polar coordinates, so we can say that the double integral over d, so here the domain is called d. So the double integral over d of the function dA is going to be equal to the integral from this to this. We put the ones that is constant first, from pi half to pi, and then it's going to be the theta here. And inside, we're going to put the integral from 0 to this function that now is no constant here, cosine. And so here we are going to write down r squared sine, that's the function here, but then we have to put r dr here. Okay, so we have then here r squared and r will be r cubed, right? And so doing the operations here, we get that this is the integral, pi half pi, and so this is integration dr, so sine is going to be a constant. I'm going to take it out, and the function r cubed, the primitive is r4 over 4. And this is going to be integrated between this and this, evaluated between this and this. Okay, so I'm going to do this evaluation first. So that will be the integral from pi half to pi, and now the evaluation here is going to be sine theta over 4, that's constant, and now I'm going to evaluate r4, so that will be 1 plus cosine to the 4th power minus 0. So this is the function that now we have to evaluate the theta. Let's separately calculate the primitive of just sine 1 plus cosine to the 4th power. So let's calculate just the primitive of this. Observe, I'm not putting any limits of integration, and just calculating the primitive, because I need to do a change of variable, right? The change of variable will be 1 plus cosine equal u, and then the derivative of this change is minus sine d theta equal du, and so the d theta equal du over minus sine. I have the du and I have the change of variable. I come here with those things, and the result will be the integral of sine 1 plus cosine is just u to the 4th power, and the theta is just du over minus sine. And now this cancel with this, and this is just the integral of minus u to the 4, which is minus u to the 5 divided by 5, and doing the change of variable, this is minus 1 plus cosine to the 5th power divided by 5. So we got that the primitive of this function is this. And so now we can come back here, and this will be then the fourth comes outside, this is 1/4, and the primitive of the function is just this that we calculated before, which is minus in front and 1 plus cosine to the 5th power divided by 5. And this should be evaluated between pi half and pi. And now we evaluate, and this is then minus 1 divided by 20, and so evaluating at pi, we have 1 plus minus 1, so this will be 0, and then evaluated at pi half will be 1 plus 0, just 1. And so the result is then 1 over 20. So that will be then the result of the area that we set up to calculate. If the function, like will be in most of the cases, is given in Cartesian and we want to calculate it in polars, that is mostly because the operation will be much easier depending on the region and depending on the function. It may be much easier to calculate in polars than calculated in Cartesian. So for example, in order to calculate this one that is given in Cartesian, everything is described in terms of x and y. How do we calculate in polars? Well, we use that x is equal r cosine y is equal r sine, and we substitute the dx dy by r. Okay, so in this case, so in order to calculate the double integral of f dA over the domain described like this, observe that this domain, the x goes between 0 and 1, and the y goes between 0 and the upper part of the circle. And so this is the domain that we need to describe now in polars. So the description of this domain in polars will be that the distance r goes between 0 and 1, and the angle goes between 0 and pi half. So we have like a rectangular description of this region in polars that is much simpler than in this one in Cartesian that was not rectangular. Okay, so the double integral would be then the double integral, where now we're going to put this function substitute by r cosine and r sine. So x squared will be r squared cosine squared plus y squared sine squared. And then we write the r and the theta dr. And so the variations here, so the variation of the angle, as we said before, is between 0 and pi half, and the variation of r will be between 0 and 1. So the integral between 0 and 1, we leave it for the end, and we are going to do the integral between 0 and pi half. We do the operations here, so we can see that this is r squared times cosine squared plus sine squared, so the whole thing is just r squared. Multiplied by this other r is just r cubed here. And so when you integrate this is a number, right? I mean, this is constant respect to the angle. And so we can take this one out of the integral. This will be the integral from 0 to 1 of r cubed that goes outside of the integral, and just the angle evaluate between 0 and pi half dr. We do the evaluation. This is 0, 1, r cubed pi over 2 dr. We take the numbers outside, and this is pi half the primitive, the integral of r cubed dr. And so the primitive of r cubed is r4 over 4. Evaluate between 0 and 1. So we have here pi over 8, and so the evaluation of r4 between 1 and 0 is just 1, and so the final answer is pi over 8.